Welcome to today's Explainer. Today we're going on a seriously thrilling, high-stakes journey. Think about a modern jet soaring along at 30,000 feet. It's so easy to just sit in the cabin, sip your coffee, and take the smooth ride completely for granted. But literally just feet away from you, inside the housing of a gas turbine engine, there's this invisible, highly complex mechanical gauntlet happening. We're going to trace the precise life-or-death path of just a single drop of fuel as it faces extreme temperatures, immense pressures, and some incredibly complex machinery. This drop has to survive a whole sequence of intense mechanical checkpoints to safely power the aircraft.
So here's our flight map for the Explainer today. We'll start with pumping and heating, move into filtering out the dangers, perfecting the spray, managing the flow, crucial safety valves, and finally tracking quantity. Let's get right into it. Section 1. Pumping and heating fuel. The starting line. All right, so our drop of fuel is pulled from the dark, quiet safety of the wing tank, right? And it's immediately thrust into the extreme, chaotic environment of high-altitude aviation. The journey kicks off right here at the engine-driven main fuel pump. Its one job is absolutely crucial. It has to deliver a relentless, continuous supply of pressurized fuel to the system. And it literally doesn't matter if the aircraft is pitching, rolling, climbing steeply, or even doing acrobatics. This dual-element pump just keeps pushing fuel forward to make sure everything runs smoothly down the line.
Now, what's really fascinating here is how the system actually uses two completely different pumping mechanisms to pull this off. We've got constant displacement and non-constant displacement pumps. Usually, a centrifugal pump, which is non-constant, sits right at the inlet. You can kind of think of this as the boost stage. Its output actually varies based on how fast the engine is spinning. And this boost stage forcefully feeds into the main stage, which is your constant displacement gear pump.
So the whole point here is the sheer exactness of that main gear pump. By definition, positive displacement means that for every single turn of those pump gears, a fixed, non-negotiable amount of fuel gets pushed into the engine. But, fuel needs fluctuate wildly depending on how you're flying, right? So this pump is actually designed to overachieve. It pushes out way more fuel than is actually needed, and there's a relief valve standing by to just bypass all that extra fuel right back to the inlet.
But wait, right after leaving the tank, our drop of fuel hits a deadly environmental threat: sub-freezing temperatures. When aircraft fuel gets down to 32 degrees Fahrenheit, any tiny bits of leftover water trapped in the fuel will turn into ice crystals. And if those ice crystals hit the fuel filters, they block the flow and the engine starves. So enter the fuel heater. This thing acts like a giant heat exchanger, using either super hot engine bleed air or warm engine oil to thaw the fuel out. It's wild when you think about it. Inches apart, you've got the freezing chill of the stratosphere and the roaring heat of the engine, working together to keep our fuel flowing as a liquid.
Moving to Section 2, filtering out the dangers, the purifiers.
Okay, so the fuel is flowing, it's nice and warm, and that melted ice is back to being liquid water. Now, any microscopic debris has to be caught before it gets anywhere near the delicate inner workings of the engine. And to really grasp the scale of what we're filtering out here, we got to talk about the micron. A micron is 1,000th of a millimeter. To put that into perspective, a single human hair is roughly 100 microns thick. So the engineering we're talking about is mind-bogglingly tiny. Just the smallest speck of dirt could cause a catastrophic failure at these extreme pressures.
So these filters, which are usually made of super fine mesh steel wire or this porous cellulose material, really step up to the plate. They stop foreign matter as incredibly small as 10 to 25 microns. But hey, remember that water we just thawed out? What is genuinely amazing is that the cellulose material actually absorbs that liquid water like a sponge. It literally stops it in its tracks. And this is vital because the fuel pump and the control units rely on the fuel itself to stay lubricated. If water sneaks past and washes away that fuel, the pump's working elements lose their lubrication and will just tear themselves apart.
All right, Section 3, perfecting the fuel spray, the art of atomization. Awesome, our drop of fuel has survived the pumps, the freezing cold, and the microscopic purifiers. But now the whole game changes. We're shifting from just moving a liquid around to prepping it for violent combustion. And spatial precision here is absolute.
The fuel nozzle is really where the magic happens. Now, older turbine engines use something called a simplex fuel nozzle, which just needed a single manifold, basically a distribution pipe. But modern aviation needs way higher efficiency, which led to the duplex fuel nozzle. This setup requires a dual manifold and a specialized flow divider, and it delivers vastly better atomization, especially when you're just starting the engine or idling. And the spray pattern it creates shows exactly why the duplex nozzle is such a massive upgrade. You see, the nozzle's job isn't to just dump fuel into the fire like a garden hose. Not at all. It injects the fuel in a highly atomized, perfectly patterned spray. This guarantees the fuel burns evenly and as quickly as possible. Because if that fuel isn't distributed perfectly, you get these dangerous hot spots inside the combustion chamber. And left unchecked, those hot spots will literally burn a hole straight through the metal liners of the chamber. No joke.
Section 4. Managing the engine flow. The flow divider.
So how does the engine manage that intricate spray pattern? Meet the flow divider. This is basically the mechanical brain behind the duplex nozzle. This unit physically routes the fuel into two totally separate paths. You have a primary flow and a secondary or main flow. When an engine is just starting up, it really needs a highly concentrated ultrafine mist to catch fire. But when you slam that throttle forward to take off power, it needs a massive roaring river of fuel. The flow divider automatically juggles these wildly different demands, and it does it without breaking a sweat.
Let's walk through the actual mechanical logic here, because it's entirely driven by basic physics, mostly pressure. When the engine starts, fuel enters an ascent exclusively to the primary nozzles to get that fine mist. But as the pilot throttles up and fuel flow ramps up, differential pressure starts building inside the unit. Once it hits a very specific, predetermined pressure, there's a bellows inside. Think of it like a tiny metallic accordion, and it compresses. That mechanical action opens a valve, which suddenly allows fuel to go rushing into the secondary manifold. By the time you're at maximum flow, that secondary line is handling roughly 90% of all the fuel roaring into that engine.
Section 5. Crucial safety valves. The safeties.
All right, so our fuel drop has successfully combusted, creating massive thrust. But what happens when the flight is over and this whole violent process needs to end abruptly? I want you to really think about this for a second. The pilot cuts the engine, the fire stops, but all those fuel lines and manifolds, they are still totally packed with highly combustible pressurized jet fuel. If that residual liquid just sat there in a scorching hot engine, what do you think would happen?
Well, it would be a total disaster. And that is exactly why we have pressurizing and drain valves. When the system shuts down, these valves immediately execute a positive cutoff. They violently trap fuel forward of the manifold so it can't move. This stops fuel from just sort of lazily dribbling into the cooling combustion chamber, because if it does dribble, you get what are called after fires, literally dangerous fires burning in the tailpipe after shutdown. That dribbling also causes carbonization, where unburned fuel just bakes onto the delicate nozzles, completely ruining that perfect spray pattern we talked about. At the exact same time, combustion drain valves just dump any leftover accumulated fuel straight out the bottom of the engine to eliminate the fire hazard and keep sticky gum deposits from forming.
Section 6. Tracking fuel quantity. The totalizer. And here we are at the final stop of our explainer. With all of this chaotic pumping and heating and dividing and dumping going on, how on earth do the pilots actually monitor their fuel supply? Well, they use this beautifully simple piece of math handled by a device called the fuel totalizer. When the plane gets fueled up on the ground, the totalizer is set to the total pounds of fuel across all the tanks. As our little drop of fuel, along with thousands of pounds of others, passes through a flow meter on its way into the engine, that flow meter shoots electrical impulses back to the counter in the cockpit. The totalizer just continually subtracts those pounds from the original number, giving the pilots a real-time running total of the fuel weight they have left. And this is absolutely critical for pilots and mechanics to understand, this system has a major vulnerability. Because the totalizer only counts fuel that physically passes through that flow meter right at the engine, it is completely blind to anything happening upstream. As our source material clearly points out, if fuel is jettisoned in an emergency, Or if there's a massive leak in the wing tank, that lost fuel is not counted at all. The totalizer will inaccurately show that fuel as still available for use. It is a pretty stunning limitation in what is otherwise a flawless sequence of engineering.
And that brings us to the end of the journey. We've traced just one single drop of liquid through a terrifying gauntlet of centrifugal pumps, micron filters, flow dividers, and pressure valves. And remember, this is all happening continuously at thousands of gallons an hour, miles above the Earth. It really makes you think, if a system this incredibly precise and complex is required just to manage a drop of fuel, what other invisible engineering marvels are working behind the scenes to keep us safe in the sky? Keep that in mind the next time you're looking out an airplane window. Thanks so much for joining me on this explainer, and I'll see you next time.